Hello everyone. My name is Hemanth Chintala. Today I am excited to share our research titled The Use of Call Graphs and Deep Learning to Improve Software Testing. This project was carried out under the guidance of Dr. Ziad Al-Sharif and Dr. Safwan Omari. Our study aims to explore how software testing efficiency can be significantly enhanced using a innovative call graph analysis combined with advanced deep learning techniques. By systematically examining graph structures derived from test executions, we have identified new ways to reduce redundancy, optimize test coverage, and prioritize testing effectively. Table of contents. Here's a brief overview of our today's presentation. I will start with the introduction of call graphs, followed by the background and related work. Then I will explain the goals of our project, the method, and the methodology we used. We will move into our experiments, results, and finally wrap up with the conclusions and the future work. Coming to introduction, software testing plays a crucial role in ensuring the reliability and quality of applications. As systems grow in complexity, testing every path manually becomes inefficient and error prone. So, that's where the call graphs come in. A call graph is a directed graph that represents function calls within a program. By analyzing these features, we can identify structural similarities and differences in how test cases execute. This is especially useful for detecting redundant and unique test behaviors, helping us optimize test suites and prioritize effectively. In this project, we explore how call graph based analysis can enhance automated software testing through graph similarity techniques. Coming to background and related work, graph similarity plays a key role across multiple domains such as software analysis, pattern recognition, and network security. Various similarity measures are used, including Jaccard, overlap coefficient, graph edit distance, and SIMRank, to capture structural and behavioral similarity in different graph representations. Project goals and objectives. The primary goal of this project is to automate test case analysis using machine learning, especially to detect redundant tests and prioritize based on fault detection potential. By representing these test cases as graphs, we can streamline regression testing and optimize test coverage. Coming to methodology and approach. Our process begins by collecting function logs from each test case. We then build directed call graphs where nodes represent functions and edges represent calls weighted by call frequency. Next, we compute graph similarity using four metrics: Jaccard, overlap coefficient, graph edit distance, and SIMRank. Finally, we analyze the results using heat maps and similarity scores to identify redundant or structurally similar test cases. Packing test cases. Here are the examples of test cases we used. They include common banking operations such as fund transfers, loan handling, utility bill payments, and insufficient balance scenarios. Each test case was designed to simulate real world transaction flows, making the analysis more meaningful. call graph experiment. In this experiment, we conducted a detailed similarity analysis of call graphs constructed from various test case executions. We applied four different metrics: Jacquard similarity, overlap coefficient, graph edit distance, and SIMRank, each offering unique insights into graph similarities. The heat map visual here specifically illustrates Jacquard similarity, which measures. Hmm, let me show you here. So, coming to this heat map of Jacquard similarity, which measures edge level commonalities between call graphs. And here the darker cells represent higher similarities. Not only for this, for all four graphs, the darker cells represent higher similarity, helping us quickly visualize clusters of structurally related test cases. For example, mm, the strongly similarity between test case 1 and 5 suggests that they share substantial structural overlap, highlighting an opportunity to optimize the testing process by avoiding those redundant testing of similar paths. Now, data set overview. Yeah. Coming to call graph experiment data set. This is our data set. Sorry. Yeah. To construct our dataset, we collected function logs and mapped them into directed graphs. Each edge is weighted based on how frequently the function was called. The dataset includes four key columns: source, from, target, to, number of calls, this, and test case here. These are the test case IDs. And going back to the presentation. Yeah, call graph experiment graph construction. Each test case graph visually, vis- as you can see here, this visualizes the workflow clearly. Nodes are the functions, edges are calls. The weight on each edge call frequency helping us to quantify the complexity of the graph. This is a visual representation of the call graph for test case 1. Mm, Again, let me show you these call graphs. Yeah, these are the graphs of each test case. As we can see, these are the nodes, saving account, checking account, external account, and these are the edges where, yeah, nodes are the functions and edges are calls. Like we can see all the 10 test cases. Yeah, this is how we have constructed the test case graphs, call graphs. And coming to call graph similarity computation, we used four different similarity metrics. This correlation heat maps compares how the different similarity metrics related to each other. We can see that Jaccard and overlap coefficient have very strong positive correlation 0.96 and meaning they often agree on graph similarity. In contrast, graph edit distance have a negative or weak correlation with other metrics, suggesting it captures a different notion of similarity. SimRank, which is based on node level context, shows moderate correlation with others. And as a conclusion, these insights are important in selecting the right combination of metrics for specific testing needs. Yeah. Sample call graph for test case 5. This is test case 5. We are using this as example to explain about call graphs. Let let's take a closer look at an actual call graph from test case 5 which involves typical banking operations. The graph clearly illustrates a sequential workflow starting from savings account followed by checking, external and utility payment account. Each node represents a distinct banking component which is directed edges demonstrate the exact flow of function calls and interactions. And analyzing such graphs visually help validate the logic of each transaction, identify potential redundant operations, and ensure the test case aligns accurately with the real world business logic. This visualization provides an intuitive method to evaluate test quality and structure. Such, we employed several graph similarity metrics, each serving a specific analytical purpose. On this slide, we focus on edge-based metrics, specifically the Jaccard similarity and the overlap coefficient. Jaccard similarity compares the commonality between two graphs by measuring the ratio of shared edges to the total unique edges across both graphs. Meanwhile, the overlap coefficient focuses on shared edges relative to the smaller of the two graphs, thus emphasizing cases where one graph is substantially smaller or a subset of the other. Both metrics provide valuable insights into structural similarity at the granular edge level, helping us clearly identify redundancy and workflow similarities between different test scenarios. In addition to this, uh, we have graph edit distance and SimRank. Graph edit distance quantifies the minimum number of changes required to transform one graph into another, thus effectively measuring structural similarity or dissimilarity. A lower GED indicates higher structural similarity. On the other hand, SimRank similarity assesses the similarity between nodes based on the neighbors, providing a context sensitive evaluation of structural relationships within graphs. Together, GED and SimRank enable a deeper, holistic understanding of how structurally related different call graphs are beyond just shared edges. This depth of analysis supports more precise test prioritization and effective test suite optimization. Graph similarity results. The results reveal several useful patterns. Here, this is the sample output table, and here, as we can see, test case 4 and 7 showed highest similarity across all metrics, suggesting redundant workflows. And whereas test case 1 and test case 5 were also strongly related in structure. Hmm. Meanwhile, test case 3 and 8 had moderate similarity, indicating partial overlap These insights help prioritize tests and optimize coverage. As I can also show you the entire complete table of the output here. This is the graph 1, graph 2, and these are the scores for comparison between each test case scores. Here we'll be having all comparison between each and every test case. Test case 1 will be compared with all other 9. Test case 10 will be compared between all other 9. Like that till uh, all. Like that we got 45 scores from 4 different similarity metrics. And coming back to here, results and summary, analysis summary. Our comprehensive analysis revealed several crucial insights. By employing multiple similarity metrics. We obtained a multifaceted understanding of the structural relationships between test cases. High similarity scores consistently pointed to redundancy and reusable structures across test cases, clearly indicating opportunities to streamline test suites and save testing resources. For example, as we have seen, test case 4 and 7 showed maximum similarity across multiple metrics, highlighting their redundant nature. Conversely, low similarity scores pinpointed unique workflows which are critical for comprehensive coverage and require separate testing efforts. This detailed analysis not only improved our understanding of test structures but also informed practical decisions on clustering similar test cases, significantly enhancing testing efficiency and effectiveness. And coming to conclusion, in conclusion, our research demonstrates that call graph based similarity is an effective tool for optimizing software testing. By identifying structurally similar or redundant test cases, we can avoid retesting the same logic and focus more on workflows, unique workflows. This not only saves time and resources but also boosts overall coverage and the effectiveness of testing processes. The results confirm that combining multiple similarity metrics provides a deeper understanding of test case relationships. As part of future work, we plan to extend this framework to real-world systems with large code bases. Integrating it into automated testing pipelines could enhance processes by intelligently selecting relevant test cases. We also aim to explore more advanced similarity models using deep learning, especially graph neural networks, which have potential to capture deeper structural and contextual patterns in call graphs. These directions will further improve test prioritization, efficiency, and fault detection. Thank you for your time. I'm happy to take any questions or comments now. That concludes my presentation. Thank you again for your attention and guidance throughout this work.